those and get them filled in so that you can turn them in. After today, I'll be looking at all of your notes, not just today's, and taking a grade for how much you completed, which hopefully is 100 because you're just completing your notes and you need to have done that to learn the material. Okay, so being that we are doing our last set of notes today, tomorrow we will review. After the review, Friday is the test. So before Thanksgiving break, we are finishing this unit so we don't have to remember it over break. I mean, you'll kind of need to remember some of these things, but you won't have to remember everything in such detail because we will have already tested over it. All right, so for a polar bond, we're just gonna first gotta learn what a polar bond is. So a polar bond forms when two atoms of different electronegativity values. So let's kind of remember what electronegativity was. Electronegativity was when we did periodic trends. So we have our periodic table here. It's a really terrible periodic table. But electronegativity gets higher as you go this way across the periodic table and this way. So going to the right and going up towards the top with fluorine right here. So it's not helium. I should really make it like that. Fluorine, this is not drawing where I really want it to draw, but fluorine is the most electronegative element on the table, okay? So electronegativity means that particular atom's attraction to be able to steal other electrons. So their ability to attract electrons to them, so they're the gainers of electrons instead of the losers of electrons, okay? So a polar bond forms when we have two atoms of different electronegativity values and they bond together covalently. Okay, so they bond together covalently, which means a non-metal with a non-metal. Okay, so when we have that covalent compound we talked about the last time we did notes, we're building those Lewis dot structures with all the fancy shapes, like this is a bent shape right here of water. So it's a covalent compound between non-metals. And if their electronegativity values are different, then they're going to result in a type of pole, where one of them is more likely to steal electrons than the other one. So this results in a pair of electrons. I'm just going to put this E with a negative symbol because I don't have as much room on the smartboard, but it's electrons. If you need to write that out, I would. These are your notes and you want to make sure you remember what it means. But this results in a pair of electrons that is shared, because remember that's what covalent does. Covalent shares, but it's going to be sharing it unequally. So even though they're sharing them, they're not sharing them fairly. They're sharing them unequally between the two atoms. The reason why they are sharing them unequally is because one of them is more electronegative than the other. One of them has a stronger pull on electrons, so it kind of like hogs the electrons in that share bond. So as an example down below, we have a bond between hydrogen and fluorine. Those are both nonmetals, and they both would like to gain one more electron to have a stable formation, so they're going to share. But fluorine is the most electronegative atom on the table, most electronegative. And hydrogen is not. It's pretty electronegative, but not as strong as fluorine. So fluorine is going to be hogging the electron most of the time. So you see how the cloud is just dark over here? It's because that electron that is sharing from hydrogen is going to be hanging out with fluorine more of the time. It's going to be hogging it. So when it is hogging the electrons are negative, it's going to have a slightly more negative charge on the side that fluorine is on, and a slightly more positive charge on the side that hydrogen is on, because it's kind of losing its electron a little bit because it's not sharing it equally. So what that creates is a pole of charge. So I'm going to kind of show you the numbers for it. So since fluorine above is a higher electronegativity value, its electronegativity value is 3.98, and hydrogen's is 2.20, so it's lower. That means that all the shared electron pair will be more towards fluorine, resulting in a partial negative pole, so partially negative over there, and a partial positive pole on the hydrogen atom. On the hydrogen end. So that's why it's called a polar bond, because it's making like opposite poles. One of the pole side is positive, one of the pole sides is negative. And that creates a polar bond. Now, molecules may be polar or nonpolar. They're not all polar, but some are polar and some are nonpolar, depending upon their molecular structure. So we can kind of tell by the shape. So those shapes we built in our last set of notes, building their shapes. This is a bent shape. There was tetrahedral. There was trigonal pyramidal, building those shapes. Okay, so based on their shape structure, we can kind of usually tell if something's gonna be polar or not. So for instance, water, okay, and water is down here In this picture, this is water, all right? That's water right there. So water, for instance, has an asymmetrical structure. That can asymmetrical means it doesn't match. Symmetrical would mean they would look the same on both sides. Asymmetrical means it doesn't. So that consists of two hydrogen atoms and two lone pairs of electrons in a tetrahedral orientation around a single oxygen atom. Now, this gives the water molecule an uneven distribution of electric charge. It's this uneven distribution of electric, and it's really not letting me write on the lines today. I'm sorry. So listen as I'm talking. But it says it is giving them an uneven distribution of electric charge. I'm gonna try to write the different color, like maybe the blue is just not giving me what I want. No, it's just not fitting with electric charge, okay? So it has an uneven distribution of electric charge, which results in a molecule that has a partial positive pole and a partial negative pole, which is a polar molecule. Okay, so let's look at this hydrogen here. So again, remember, oxygen's in the center, and it's bonded to two hydrogens, H2O. When we did this shape in our previous notes, oxygen has 6 valence electrons, hydrogen has 1 each, but there's 2 of them, so plus 2, so I have 8 electrons that I have to use. The next rule says that when they're bonded together, each bond is made of 2 electrons. So that's 2, look like a double bond. So that's 1, 2, 3, 4. So I've already used 4 of my 8, so I have 4 left. And then it says to put them on the outside atoms, except we never put them on hydrogen. So even though I want to put those 4 on my outside atoms, I never put them on hydrogen. So I actually skip that step. And it says if you have any left over, which I do, I have 4 left over, they go on the center. So it ends up being dot, 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 dot on the center. Now, how that looks in our PhET lab that we did, we actually got to build the shapes, like what it actually ends up doing is you have oxygen here and hydrogens. All I did was put the hydrogen on the bottom this time. And these electrons up top, those are called lone pairs of electrons. Remember, electrons don't like to be near each other. They're both negative. So these electrons and these electrons don't like to be near each other. So they're repelling each other. Negative, negative repels each other. It also is repelling these electrons in the bond. Remember, those are 2 electrons as well. So it's repelling the bonds, they're repelling each other, and that's why it makes this weird bent shape, because all those electrons are repelling each other, which is what we learned about in our last notes, was how to build those shapes. Is called the Vesper model because it stands for valence electrons repulsion. Okay, so they're repelling each other and they make these weird shapes. So these hydrogens are being pushed down by these lone pair electrons, making them bent. Now, when I'm looking at that, you can notice that it doesn't look symmetrical. I have lone pairs up top. I have atoms on bottom. I do not have like atoms all the way around the oxygen. It's very unbalanced looking. So it's called an asymmetrical structure. When a covalent compound is asymmetrical, usually they're going to have an uneven distribution of electric charge, or they're going to have a positive and negative end. So I'm looking at this one. Oxygen is a stronger polar. It's just like the second most strongest atom on the table for electronegativity. It's right next to fluorine. So it's hogging the electrons and becomes negative. The hydrogens are losing those electrons again. I'm losing them more to the oxygen, so I have a slight positive charge. So you have this slight negative at the end, slight positive at the end. That's what water does. Water is a very polar molecule, and we're going to learn more about water later in the year, but it affects all the cool properties that water does. We don't know much about it. We have a whole unit over water, but water has a lot of cool properties that are due to the fact that it's polar. All right, now molecules like carbon tetrachloride, let's go ahead and scroll down so we can see that. Molecules like carbon tetrachloride, which is what this picture is, and I'm now erasing off of what we just written. There we go. Okay, so carbon tetrachloride, looking at this one, however, is symmetrical. It's symmetrical structure. It has a very balanced shape. It has a carbon in the center, and then it has chlorines all around it, 4 chlorines. That's carbon tetrachloride, because tetra actually means 4. So there's 4 chlorines, carbon tetrachloride, 1 carbon, 4 chlorines. And they're bonded like that, and they have the full valence electrons around them. But because they are balanced, there's a chlorine on all sides, and they're all pulling the same amount, and all these are chlorines. All these chlorines are pulling the electrons the same amount. No one's pulling more than the other one because they're all the same atom. That makes it very symmetrical. If they are all pulling the same amount, then they are sharing evenly. They're sharing equally. They're going to have an even distribution of charge. So that makes it a non-polar molecule because we have that even distribution of charge. No one's pulling more than the other. So we don't have a positive negative end. They're just a molecule. It doesn't have a charge at all. So in general, molecules are non-polar if there are no lone pairs. So if there are none of those lone pairs like these, remember these are the lone pairs that are on top of oxygen. If there's none of those, there's none on this one, no lone pairs here, or if all the peripheral atoms, all the atoms on the outside, so all the outside atoms, that's what peripheral means, all the outside atoms, if they are the same element. So like in this case, they're all chlorines and there's no lone pair, so that made a balanced molecule. They're all sharing the charge equally, so it's non-polar. Whereas up here, in this example, it had lone pairs, pushing the hydrogen just to one side of the atom, so it made it not symmetrical, so that it is polar. Okay? I'm going to scroll down. We'll fill out this chart. Now, if you have an electronegativity chart, you don't have to look at the shape. So one way is to look at it like that, look at the shape, and then we can know. The other way is just to look at an electronegativity chart, which you have in your notes. Okay, so we have one here posted for you, and I'll give you those charts. I won't make you memorize those numbers. But if you're looking, all these numbers on the chart represent the electronegativities that those elements actually have. Okay, so I'm going to scroll up. And then you can look at this chart up here to see what they need to equal. So if the electronegativity difference means subtraction. So you're literally going to subtract the difference between the two atoms' electronegativities from this periodic table down here. So if their electronegativity difference is 0 to 0.39, so not very different, then that makes a non-polar covalent compound. Okay, so non-polar covalent compound if their electronegativity difference isn't that much, because no one's going to be hogging the electrons because there's not that much difference in their ability to pull the electrons. Then if there is 0.4 to 0.99, it's going to be moderately polar. So you're going to have a slight negative end, a slight positive end, but not much. If they have a difference between 1 and 1.99, that's highly polar. Water falls into this category. They have a very, like a positive end and negative end, and it affects a lot of the properties that it possesses. If it is 2 or above, that actually is ionic. Remember, in ionic, they gain electrons or they lose electrons entirely. Like they literally, like one of them gives up an electron, gives it away completely, never gets it back. And the other one gains it, so they get a positive negative charge completely, so obviously they have a charge. So that's not polar, they just have charges. These polar versus like a little bit polar, so moderate polar versus highly polar, means that they don't completely have a charge. They don't always possess that electron that they're sharing unevenly. They just share it unevenly most of the time. So that means that they have a slight negative charge compared to a completely non-polar one who doesn't have a charge at all. All right, so let's do this practice down here. Let's see what the answers are. So I'm going to scroll down. We're going to find the two atoms on the chart, figure out their electronegativity difference, and see if they're polar or not. So H and F. So hydrogen and fluorine. So hydrogen's number is 2.20. And actually, I don't usually like to write it there. Usually like to write it over here. So this is hydrogen's 2.20. And then on fluorine side, fluorine is, remember, it's the highest, 3.98. And then when I subtract those two numbers, so 3.98 minus 2.20 is 1.78. That's the difference between them. So fluorine has a difference of 1.78. That's how much stronger it is. That falls into this category, 1 to 1.99. 1.78 is in between that. So this molecule is highly polar. It's definitely pulling the electrons more towards the fluorine. Then we have NaCl. So Na on the table is 0.93 electronegativity, pretty low, and chlorine is 3.16. When you subtract those numbers, so 3.16 minus 0.93, you get 2.23. Well, that falls here. That's not even covalent. They're not even sharing at this point. Sodium is going to give its electron to chlorine because the chlorine has such a strong pull compared to sodium. So it just totally gives it up, and it actually makes an ionic compound. It's not sharing at all. It's making an ionic compound, giving and taking, becoming positive and negative. And lastly, we have bromine versus bromine. Well, that means it's a compound between bromine and another bromine. So that would make 2.96 is the electronegativity of this bromine. Well, there's another bromine that's also 2.96. So the difference between those two is 0. They have the same electronegativity. So neither one of those bromines is going to be pulling the electron more than the other. They're both pulling the same amount because of the same atom. So that would make a non-polar molecule. Okay, I didn't give an example of this one, but you'll see one in the practice. If it's in between those numbers, then it's moderately polar. All right, and that is how you do it. That is the end of notes. We will review tomorrow and be testing on Friday over this material.